Welcome to the first part of our fourth unit. This is the beginning of what I typically call Mathland. So the unit 4 is very much giving you some math skills that you're going to need in order to proceed with physics. And to help motivate that, what I want you to think about is right now, you can do position, velocity, and acceleration. You can do projectile motion in one dimension, which is great as long as all you want to do is play catch with yourself. But if you want to throw a baseball with a friend or football game or something like that, you need 2 dimensions. And so we have to develop the math in order to make those 2 dimensions happen. And the first step of that, as a little bit of motivation, is this YouTube video. And it's 3 minutes long. I'm not gonna play the whole thing for you. Here it is. You can come back and click on the link anytime you want, if you will.
It's an old video
but
which
what we have is a gentleman who is dropping a ball.
Almost nothing.
And he looks
If we slow the video down, then we can see that the ball accelerates under the force of gravity. If we reverse that and then play it again frame by frame, we can see that the distance the ball falls every frame, which is every 1/25th of a second, increases each frame. If we eliminate the blurring around each image, place all of those images onto one frame, and then mark the centers of each image, we can see that effect more clearly. If we throw the ball horizontally from about the same height, then again it's difficult to see. With the video slowed down, we can see that the path is curved as the ball is accelerated vertically. The precise track is more obvious if we put all of the images onto one still. If we then combine that still with the first one we took of vertical motion onto one photograph, the comparative heights at each frame can be seen. If we draw lines across, you can see that the center of one ball matches the center of the same ball thrown sideways.
Okay, so I'm going to encourage you to go back and watch the last half of this video on your own. I also look on the up next, and there's a similar video about the independence of the motion in 2 dimensions. And that's what we're trying to get at here. And that's when we're dealing with 2-dimensional projectile motion, we can treat what's happening horizontally separate from what's happening vertically. Okay? But to do that, we need more math, and we need better ability to keep track of our vectors and what's going on with them. Okay, so review really quick of vectors versus scalars. Remember, a vector is something with a size, otherwise known as a magnitude. You can use those 2 words interchangeably, and a direction. Whereas a scalar just has a size. Okay, one is just a number, the other one is a number with an associated direction. Oftentimes that direction is a positive or negative, but it could be something else, north or south. You could even specify an angle, which is what we're going to be moving into. Okay. Thus far, all of your work has been with a single axis. Typically, we've left that be the x-axis. Sometimes it's oriented horizontally. Other times it's been oriented vertically, depending on what the needs of the system we were looking at were. In this case, we're going to add another dimension. And for that other dimension, typically what we do is we let the x-axis be our horizontal motion and our y-axis be vertical motion. And typically, positive to the right for x, positive up for y. This is not set in stone anywhere. You can rotate them and do all sorts of things. A couple of units from now, when we get into friction, we're actually going to want a coordinate system that does this, where it's tilted on purpose. But the key thing here is that, to the best of my ability, my x and my y axes are always perpendicular to each other. Not this semester, but next semester, we're going to have some things that require 3 dimensions. And when we do that, we would add what is known as the z-axis, and z would be perpendicular to both x and y. If you're looking at this, that means z has to be coming into or out of the screen you're looking at. But again, that's for next semester, 202. So we can view any vector as the sum of 2 vectors. Okay, so if I have a vector A, I can write it as a vector B plus C. So let's pretend for a moment that vector B is going like this, and vector C is straight up. If I want to add these 2 vectors, then I take and draw, to the best of my abilities, to draw B again. I draw the first one. Then to the tip of the first one, I add the tail of the second. And then the sum of those 2 goes from the tail of the first to the tip of the second. And this would be the vector A. So I can view a vector as the sum of vectors. And I said 2 originally, but technically I could add as many together as I want. Okay? Now, you can see this. The next slide has us going to look at a simulation. And I already have that simulation open here. We're going to go to the Explore 2D tab and draw ourselves a couple of vectors. So the last time that moves the coordinate system. Let's grab a vector B, toss it down. Grab a vector C. Oh, C is going straight down. The example we just had a minute ago was C going straight up. So I'm going to do that, and then I'm going to put it at the tip of B, and I'm going to click the Show Sum button. And they called the sum S instead of A, but that's okay. See how it goes from the tail of the first to the tip of the second? And it gives you all these numbers up here at the top, okay? So we'll go through them bit by bit, and not all of them will make sense at the moment. But by the time you're done with Unit 4, they should. And if they don't, I suggest you go back and watch Unit 4 again. The S in absolute value signs, that tells you the magnitude, the length of the vector S. Theta tells you the angle that is made by the vector S relative to the positive x-axis. So if I grab this guy and put him there, and angle 61.9, just agreeing with what's above. SX, this is the piece of X that is parallel to the x-axis, known as the X component. And S sub Y is the piece of Y that is parallel to the y-axis, known as the Y component. And now I can view the vector S as the sum of the components, SX plus SY, just like we looked at S being B plus C. Okay. And it'll show me the components. There they are. Okay. You can come back and play with this simulation as much as you like. The link is right here. Okay. So, with this knowledge of vector addition that we now have, if I have a vector v, which is the sum of 2 other vectors, v1 plus v2, Does V necessarily have to be greater than V1 or V2? Okay, so one thing to notice. Every V in this portion is bolded, and every V in this portion is not bolded. Okay. The reason for that is because this statement is vectors, and this statement over here is asking about only the magnitude. And when typing in a book, it's really hard to put the arrows over the top. That's not normal typeface. But bolding is easy. So they use the convention that if a variable is written in bold, it's a vector. There you go. Okay, so if I have a vector v, which is v1 plus v2, does the size of v necessarily have to be greater than v1 or v2? Okay. Well, think of hopefully obvious examples. If v1 is this way, it's got a length, let's see if we can do a length here of 4, and v2 goes the other way, also of length 4, and I add those two together, what am I going to get? This results in v equaling 0. Is that greater than v1 or v2? Not at all. Both of v1 and v2 have a magnitude, have a size of 4, because we set it up that way. V is 0. Okay, so that's one way I can get an answer of something not bigger, right? So one thing to keep in mind is that when we say vector addition could mean that we're subtracting. It just depends on the directions. Okay. So if I have two vectors of unequal magnitude, so of unequal length or unequal size, ever add up to give the 0 vector? Okay, well, if I have, again, a vector of length, looks like this one's going to end up being length 5, so let's call that one A. And I have another vector that isn't the same length that I'm trying to get to make the 0 vector. If A can't be the same length as B, can those ever equal 0? So the answer to this one, I hope you see, is no. What if I have 3 unequal vectors? So now if I take and put in a third vector of length 1, so C, oop, I lost my arrow there. So now if I think about the vector D being A plus B, where A and B do not have the same length, that's the solution to the first question. Now I'm dealing with D equals A plus B plus C. And can those equal 0? Well, I started at this point, came back to that point. So the answer to the second portion here is yes. Okay. That continues, or that concludes this portion of Unit 4. In the next portion, we're going to work with trig functions and Pythagorean theorem in order to develop the math we need in order to get those vector components.